Okay, so we're continuing on from yesterday. And we talked yesterday when we have two events, they might be mutually exclusive, they might not be. And now we're going to look at compound events and whether events are independent or dependent. Okay, so that's sort of more terminology that we have to figure out, and a little bit different way of calculating. So independent events. So A and B are independent if the occurrence of A does not affect the probability of B. So two events, could be more than two events, but we're going to stick with two. And does the probability of the first thing happening affect the second thing? So an easy example would be if you had a bag of red and blue marbles, and you wanted the probability, and we'll do one similar to that, of choosing two red marbles. Okay, well the first one you choose, okay, you know that if they're 5 and 5, then that's probability is 5 out of 10, so a half to get the first one. But if you do not replace that marble, then there's only 4 blue left in the bag out of a total of 9 marbles. So to get the second one being blue, it's 4 out of 9. It's not the same probability each time. So that's what we call conditional probability. Okay, so or conditional probability is sort of the name for the whole thing, but the events are dependent events. It depends what happened in the first draw. Okay, so here we're going to tossing a coin and rolling a die. They're independent events, since the outcome of the coin toss has no effect on the outcome of the die. Right? They're not the same. It won't affect what happens to the next. It does not change how many sides on a die or anything like that. Sample space is written out for you. Okay, so heads and all the sides of the die, tails and all the sides of the die. You can do that with a tree diagram or just write them out. So if a coin is tossed and a die is rolled, then the probability of getting a head and a number less than 3. Okay, so head and a number less than 3 would be those two there. You can just look at your sample space. And there's a total of 12 possible outcomes, so 2 out of 12 is 1/6. So if you know the outcomes, just count them up. Okay, now let's look at separately what the probabilities are. So if you toss a coin, probability of getting a head is 1/2. And if you roll a die, the probability of a number less than 3 is 2/6. You multiply, stop listening please. You multiply 1/2 and 1/3, you get 1/6, which is exactly the same. Okay, so if they are independent events, you can multiply the probability of each event together. Okay, so if A and B are independent events, then the probability of A and B, or you can use the intersection symbol, is the product of each individual probability. Okay, so if a card is selected from a standard deck of 52 cards, then replaced before a second card is selected, what's the probability of getting a queen and then a king? So the probability of getting a queen is 4 out of 52 in the deck. You can reduce it, but I'll just do that for now. It's put back in, so there's still 52 cards in the deck. If it wasn't put back in, then probability would be different. It would be dependent. Okay, there would be only 51 cards, but it is put back in, and there's 4 kings out of 52. Right, so that's really 1/13 times 1/13, which is 1 over 169. Okay. So even though we're dealing with a deck of cards, okay, the actual event of getting a queen and a king are independent. That getting a queen is not going to change getting the king if you replace the cards in the deck. Okay. So let's look at ones where we have to consider that. So conditional probability for two events A and B, that vertical line, so again, you have to know the context of the question. So A, vertical line B, is used to represent A occurs knowing that B has occurred. Okay, knowing or given, sometimes we say given that B has occurred. Okay, and so A given B. So probability A, given that B occurred, is the probability knowing that B has occurred. So here, basically, we'll do it in a Venn diagram. It's reducing your total number of outcomes. Okay, so it's kind of like the overlap in a Venn diagram. Okay, if you are trying to find the probability of A happening, that there has to be out of now the probability that B occurred. Okay, so what do you do in terms of a formula? You find the probability of both of them happening and divide it by the probability of B happening. Right? This is now your total cases, total probability. Okay, so it's easier to see when we do an example, a little bit harder with looking at the formula. This is just the rearrangement of the formula. Take a look here. This has probability of B given A. So these are just different versions depending on what you're trying to look for. Okay, obviously the order of intersection of two sets doesn't matter. A intersect B is the same as B intersect A. This order does matter. So if we were to solve here for P of B given A, we would get probability of A intersect B over probability of A. So whatever that, guys, stop talking please. Whatever that given event is, that's the probability in the denominator. Okay, those match up. These match up. Okay, now you will be given the formula, so you don't have to memorize it, but it's sort of nice to be aware of that. Okay. So dependent events, A and B are dependent events if the occurrence of A does affect the probability of B. So here's an example. Selecting a card from a deck and then selecting a second card without replacing the first. Okay, those are going to be dependent events. So if the card is selected and not replaced before a second card is selected, probability of getting a queen and then a king. So I'm asking for the same probability, but now the actual situation has changed. We're not replacing that first card. So that's why now the first one is probability of a queen. So that's 4 out of 52. And the second one is the probability of getting a king given that the queen was picked. Right? So that's when it's in this form here. So that kings, there's still 4 kings in there, but now there's one less card in the deck. Okay? So 4 out of 51. That's the same as 1 out of 13 times 4 out of 51. So what's that? 4 out of, use my new type of calculator here. Okay, 1 over 13. Let me do it this way. I'll just do 13 times 51. Okay, 663. Okay. Next one, a box contains 5 red and 3 yellow marbles. If 2 marbles are selected without replacing the first, then determine 2 reds. Okay, so 2 reds, well, the probability of the first red, well, the total here is 8. So 5 eighths. And then the probability of the second red, we did not replace it. So now we've chosen a red. We only have 4 left out of 7 marbles in there. Okay. So that's 4 goes into 8 twice. So that's going to be 5 over 14. Sometimes we'll ask for fraction form, always lowest terms. Sometimes we'll ask for decimal form. We'll say what to round to, probably the nearest 100, 80,000, just to be pretty accurate. And then sometimes we might say percent. Okay, red then yellow. So that's going to be red, 5 eighths. We've drawn 1 out of the deck, so it's out of 7. And the next one is yellow, and there's 3 yellow. We haven't chosen it. Okay, so notice how the second fraction has a denominator 1 less, because we're not replacing that marble back into the bag. Okay, so red and yellow, that can be red, then yellow, or yellow, then red. Okay, so in this case, we're going to have to do, so red and yellow, we can do the red, then yellow that we already did. We can then do, so really this is red, then yellow, and then plus probability of yellow, then red. There's different ways to do this, but this is the way, because of the order that we've done it already, we can do this. So probability of yellow would be 3 eighths times 5 sevenths. So notice how they end up being the same. Oh, yeah, 5 sevenths. Okay, same, that's going to end up being 15, 56, which is 30, 56, which is 15, oh, more 6 goes into that, sorry. Let's see, 2, so 25, 28. All right, so then we're going to look at Venn diagrams. You learned about Venn diagrams partially on your own at the beginning of the semester, and then we reviewed some questions together. Now we're going to use Venn diagrams as well for probabilities. All it means is what the numbers in there are now probabilities rather than the number of people. Okay. In the first one, though, it's number of people. You can tell. Remember, probabilities can't be more than 1 unless it's a percentage. So it says in this one, a survey was conducted to determine whether students were currently taking math and or physics. The results are displayed in the Venn diagram. Okay, so these are numbers of students. So how many students participated in the survey? So just take a look and make sure there's something listed in each part. Well, I guess if something wasn't, then you would assume that it was 0 because it looks like this is the final Venn diagram. So add them up. So 10 plus 30 is 40, plus 40 is 80, plus 20 is 100. Okay. Oops. Yeah, go right now, Mike? I'm almost done. Okay. So what's the probability of a student taking both math and physics? So remember, the and is the overlap. So here, that's the math and physics. So these students take just math, these take just physics, these take both. These don't take either. Okay, so 40 out of 100. Okay, so that's what, 2/5. Okay, you can convert it to a percent if you're asked to. So what is the probability that a student, takes either math or physics, but not both? So, or means the hub, everything. But it says, but not both. Okay, so that means we're going to not include the 40. Okay, so that would be 30 plus 20 is 50. We're not going to include the 10 because they don't take either of them, right? And given a student is taking math, what is the probability that they are also taking physics? So now, so really what this is asking, I go back. So probability of taking physics, given that they're taking math. That's what we're looking for. Okay. So if we were to use a formula, that would be probability of physics intersect math over probability of math. But we don't need to use the formula. We can look at our Venn diagram. Remember I said it makes it really actually a lot easier to think about it. So given that a student is taking math, so now all I'm going to look at is this circle. That's the given. That's my sample space. Given it that they're taking math, what's the probability that they are also taking physics? That would be these. So that would be 40 out of 70. So this is 40 out of 70, which is 4 sevens. Okay? You don't care about everyone other than those taking math. Now, if you use the formula, then intersection of physics and math is 40 out of 100 if we're dealing with probabilities, right? Probability of math is 30 plus 40 is 70 out of 100. You simplify that, the hundreds divide out, you get 40 out of 70, which is 4 sevens. So you get the same thing. You want to use the formula, but if you've got a Venn diagram, just go to what that given statement is, given that they take math. All right, and then the last one, again, is Venn diagrams, just to show. So remember we talked about the complement, that prime symbol means the complement. So use Venn diagrams to show that the complement of A intersect B is equal to the union of the complement A and complement of B. So Venn diagram, we're going to do 2 of them. We're going to assume that they are non-mutually exclusive. So there's the sets that overlap. Okay. This would be A, this would be B. Okay, so A intersect B is the overlap. the complement of A intersect B is everything except that overlap. Okay, so if I highlight that, then the complement will be all the white portion of that rectangle. Okay, so here, up there, anyway. So this would be all the white. Okay, the blank, what we haven't selected, is the complement. Okay. Now, if I look here, the complement of A is everything outside of A. So that's going to be, maybe you want to just shade it with, say, I'm going to use diagonal lines that go to the right, and then I'll use a different color. Complement of B is everything not in the B circle. So that's, I'll use red and go this way. Oh, sorry. Yeah, not in the B circle. Okay, so the union then, union means everything. So everything that is shaded with blue or red for me, if you use pencil. So everything that's shaded is the union. And so you can see that is everything except that overlap. Well, this was everything except that overlap. So these are the same. Okay, so here, this is all shaded portions. Okay, so here, everything except that overlap. Okay, so that's it. Now it's practice time.